Okay, so talk today here is about one method of porting deep nets to spiking accelerators. So it's been pretty well discussed already why we'd want to do this, or why we want efficient and or local inference. And there's obviously a bunch of constraints that we want to meet: power, latency, bandwidth. Sometimes interference is an issue in various applications, military, security. And then there's various ideas about what will be the killer app. And obviously there's probably a lot of near-term things. My idea is I think that maybe advanced neuroprosthetics, although that's a little bit further in the future, would really be a killer app, because not only would it need to meet a lot of the usual requirements of power, latency, thermal, and privacy initially, it would really benefit from actually being able to speak the language of the brain. Because, I mean, especially if you want like a two-way link of some sort, but that's getting off into sci-fi right now. So, but today we have deep nets, mostly. And of course, these are all tensors, matrix ops. And of course, there are nice accelerators being developed for that. But then we also have all these new spiking accelerators or event-based systems. And it's a little less clear how to port traditional deep nets to these new platforms. So that's what we're going to look at, or at least one method of doing that today. Now, I realize there are at least a couple different methods that have been explored, but what specifically we're looking at here is what is the most direct way you can run them on specific hardware platforms like Spinnaker or Luihi, where things are basically discrete event-based. So there's a few different issues owing to the differences between traditional artificial nets and spiking or event-based. I mean, on the one hand, we have continuous activations versus discrete events. We have global clock-driven synchrony that we require for ANNs versus, we try to leverage local event-driven asynchrony in that time model itself. We've got these dense tensor or matrix representations, and whereas we now want to sparse synapse and neuron representations. Oftentimes there's, we don't always have floating point, although Spinnaker 2 is apparently going to have floating point, which will be interesting. Although it matters little. I mean, quantization is something that's been pretty well explored already. Sometimes there's issues like, so you have biases in traditional nets, and it's not always clear the best way to map those to the spiking hardware, depending on what framework. Like we'll see that a little more. Like, for example, if you're using Pine and you have populations that have that all kind of share the same threshold, how do you interpret biases? Well, there's a few different ways. And then you have weird things like batch normalization layers, where it's not necessarily clear what to do in the conversion. Now, as far as converting from continuous to binary activations, so addressing that first issue, one way to do that, which is a little different than a lot of the approaches that that are generally taken, where you go to a rate code. Rather than that, what happens if you just want to quantize your deep net so that the activations are just binary? And that's one shortcut to being able to run them. Now, to that end, we have a method we've developed at Sandia called Whetstone, and it basically converts to binary activations in sort of during training. After you've initially trained your net, you slowly change the activation functions in a layer-wise fashion. So if you have a feed-forward, just sequential type of net, you start at the first layer, and you gradually sharpen your activation until it's a step function. And you do this slow enough that the net has time to adapt to those changing activations. And by the time you finish the last layer, the thing doesn't learn anymore, but you're done, and you have a binary activation quantized version of your network that preserves a good bit of the accuracy. And what we'll see is one advantage of this is if you run them like a standard net, you potentially have advantages in terms of throughput, because you don't actually have to count pulses over time. It's pretty much a one-pass evaluation. And you can have multiple, if you've got a multi-layer net, you can have several different samples being evaluated at the same time as separate kind of wave fronts propagating through your net. And you don't have to wait around to count anything. So it's not quite, it's sort of not really rate coded. So kind of in the spirit of Fugu, it's a bit of a hack. So this is an animation where the white bar here is supposed to be this is the spiking accuracy if you were to, or binary accuracy if you were to immediately just convert all the activations. And these are like different layers. And then you've got the non-spiking accuracy here. And as you sharpen, as you can see this getting sharper, approaching a step function, these beta much converge, and this one is pulled up towards where the non-spiking accuracy is. And then, of course, by the end of the process, they're the same because we're basically evaluating the same two nets. So it does work somewhat. And we have applied it to various other problems besides MNIST. We've used it for semantic segmentation, and that's just video of that. We have made an MNIST autoencoder that worked reasonably well. And we also played around a bit with cart pull and Q-learning. Now, today, we're going to particularly look at how would you port these types of nets, or like whetstone sharpened nets, as we would say. How would you port that to Spinnaker? Now, of course, Spinnaker is event-driven, uses multicast packets with fixed routing tables for efficiency, and we'd like to leverage that. We'd also like to leverage the local synchrony, since each of these cores has their own clock. Even though it's globally asynchronous, you can still time events. And there's obviously, they talked about on Loihi, there's a mechanism that achieves the same thing, works a little differently, but you nonetheless have some guarantees. Like if you need something approximating global synchrony, you can get that. So we do have some results at this point, which we'll go into how this was achieved. So to start out, we wanted to see, could we max out a Spin 5 board, a 48-chip board? So we managed to use all available cores on our particular board and all the chips. And after I/O routing, loading, because we're running all this through an Ethernet port that's rather slow to load the data. So, but once everything is loaded, though, into the chips, it buffers the inputs into the SDRAM if you're using a spike source array. The actual inference only took a little over 0.6 seconds for binary MNIST, all 10,000. So it's a very high throughput you can get with that. But and more importantly, it demonstrates that you can, in fact, run what started off as traditional nets. Now we have a larger example. This is actually what would be more properly a deep net, involving convolution, max pooling, as well as dense layers. And for that one, we started to get into some engineering expediencies to make it function, which we'll talk about. A little bit lower throughput, but we did get a pretty good accuracy for binary MNIST, mind you, because you can't, when you binarize it, you round, you can't always tell the difference between some of the digits. So the ceiling on your accuracy is going to be a little lower anyways, but 98.1% on MNIST, not bad, and involved convolution, max pooling, and we ran it on Spinnaker, pretty much just train the net, run, just load it right over, got a pipeline. So that pipeline looks more or less like this. So we use whetstone to turn the nets to binary activations. We remove the batch norm layers by merging them into the weights and biases. We convert the tensor to sparse representation. We replace the biases with explicit bias neurons, which will explain why we have to do that. And for the convolutional net, to avoid congestion, we use a trick, time division multiplexing, which takes advantage of the propagation delays buffers in order to avoid congesting the packet system. And then, of course, you have to convert it to Pine and then run it on Spinnaker using the Spinnaker library, which, of course, takes Pine. And many of you who work on this will know about this. So briefly, removing batch norm layers. I mean, when batch norm is done training, it leaves behind this linear transform that uses sort of the average variance and central tendency from the online batch norm, and as sort of to keep things consistent. And so we pretty much just take that and we merge it back into the weights and biases to get rid of that layer. Pretty straightforward. Now, going from tensors to neurons. Well, obviously, convolution is a bit difficult there because a literal neuron interpretation or biological interpretation of convolution involves an awful lot of neurons. And you're going, I mean, yes, there's not a lot of parameters, but every single stop you make, every convolved step is basically a separate neuron. And yes, there are mechanisms you can share the weights perhaps if you optimize your firmware and whatnot, but you nonetheless have to keep track of all these states and have to evaluate them all, which is going to be costly on any platform. Of course, max pooling maps pretty nicely because it's really just an OR gate, which works just fine as a threshold neuron. So we just convert that sparse. Not a big deal. Reducing the percentage of the weights, this has been well explored. You don't really have much of a problem going from floating to fixed until you get to relatively lower precisions. And this is all in, if you're curious, this stuff is in, we'll have a link to the paper, the Whetstone paper at the end where this results is all presented in a little more detail. Okay, so biases. So as stated, in Pine, this is all population-based. So if each layer is going to be a separate population, then it might be tempting to interpret the biases as thresholds for firing on the neurons. The only thing is Pine wants to reuse the same template across all the neurons. So what we do then is we just add a bias neuron and just have those in the connection weights, and we just daisy chain them so that each bias neuron will trigger the next one in the line and provide the proper bias input at the right time. Now, the one thing I need to mention, we had to use to do this on Spinnaker, we had to use a special neuron that decays instantly back to 0 as soon as, at any time, on any time step. Inputs come in, it either fires or it doesn't, and then whatever potential's in there immediately decays to 0. So that was the only customization we had to do, which is pretty well documented how to do that sort of thing, how to create a neuron template. But yeah, so basically your bias neuron triggers the next one, and at each time step, everything decays back to 0. Right. Now, to get around some of the congestion issues, because when you start to have really large fan in and fan out, and you have these synchronous bursts of activity that all hit at once, it can overwhelm the routing system in some cases. It's not entirely clear why, and this would be a question for Steve, perhaps afterwards. But basically, to get around this, we use time division multiplexing, where we pretty much just stagger the firings of the neurons in different population and just have the timing with the weight delays, the propagation delays, such that the neurons all receive their input synchronously when they should, so they produce the correct firing behavior. For convenience, you can have your output group be in this, just one temporal group. So we have an animation here which illustrates this, make it a little more clear. So when you see these things flash green, that's actually when the packets are being sent in Spinnaker. And then when you see these are actually the packets being buffered in the ring buffers on the receiving cores. So once fired off and delivered, they just sit and they wait in their destination. So they don't cause congestion. And then you'll notice how the last group they're all in the same temporal group. So the spikes all converge at once, and the entire thing fires at as it should. Well, we're showing them all firing here just for the sake of illustration, but obviously not all of them are going to fire, right? Now, yeah, so this is basically just explaining why that works. So, pretty much this number represents the time step at which the neuron fires, and here we just simplify. We have like 3 temporal groups and 1 neuron per layer per temporal group, just for illustration. And I just have the delays that are necessary, just color coded. But you get the correct result of evaluation from that. But yes, without this technique, we were not able to put any kind of anything other than like a non-trivial convolution that would actually function on that. This will be explained more. And we're going to have a proceedings paper in all likelihood, which will go into more depth on some of the caveats, so there are some performance considerations. I'm not sure how much of this will apply to Spinnaker 2. Spinnaker 2 is, at least from literature we were looking at, the prototype in anyways was clocked at a higher rate. Not sure about the communication fabric. But there's this application called the delay extension vertex that if you have more than 5 temporal groups in the scheme we've described, then you end up needing a delay that's greater than 10 milliseconds, which in our experiments would trigger the need for a delay extension vertex, which is this, so because like locally there's only so much memory that the ring buffers have allocated. So in order to get beyond that limitation, they actually will have the spikes routed to a temporary core where they'll be held and sort of buffered for longer periods of time. And there's various performance trade-offs for the way that works currently. But so basically, there's a lot of unknowns still, and there's definitely a lot of room for changing firmware. I've seen other papers where convolution was implemented, at least on some rather small nets. They used weight sharing, and they buffered they stored the synapse matrix weights and in the actual most local memory, which is the data tightly coupled memory on Spinnaker, which is really fast, but not very plentiful. So, yeah. Let's see here. So, future work, obviously. We've only just begun to explore real-time I/O. Right now, these experiments, the results were we just pretty much loaded everything, like I said, through the Ethernet, and then it has to be distributed to all the chips through like system-level packets before it actually can run. So obviously, the Spinnaker has much quicker interfaces available, like spin-link interfaces and such. We'd like to work on that. There's also the issue of input encoding methods, because when you interpret your nets as binary activated spikes, then you pretty much have to format your input to be perfectly synchronous and binary as well, unless you want to have your first layer, sort of your transduction layer, implemented somewhere else, like maybe in a traditional or GPU accelerator or processor. But if you want direct binary inputs, there are a variety of techniques. One is obviously you can just code it binary and take your weights and sort of split them off logarithmically into smaller weights based on the significance of each digit. A general idea that was suggested by Mike Davies, like last summer, or Telluride. The other thing we'd like to look at is, because like recurrence is not quite clear, best way to train recurrent nets on when you are turning your activations binary, and essentially the gradient doesn't flow back through. One way to possibly get around this might be a kind of pseudo-recurrence where you can explicitly train the net to take input from itself and try to make better decisions on that sort of iteratively. And such pseudo-recurrence could be used, say, for processing a large image in little patches. So sort of like where in the example where we have the tiles of 170 different versions of a small dense net run across all the Spinnaker chips on the Spin5 board, we could divide up an image, for example, and feed pieces of the image to the different tiles. But then the tiles could actually communicate across with each other and sort of in a recurrent way, where iteratively they produce better results from using their neighbor's context. Pretty straightforward. And of course, we're looking forward to Spinnaker 2, which just based on if the clock rate is in fact 500 gigahertz, that would immediately deliver about 2.5 times speed up, along with other potential optimizations. Yeah. So here's references if anyone's curious. And if you're wondering, the Whetstone is open source and is available at this link here if you're curious to play with that method for binarizing your activations. And we also have a paper. You can find that at this link as well as it's in the archive. So yeah, so I guess we can take questions now.
Thank you very much, Ryan.
Yeah.
Open for questions.
Yeah.
Stop.
I mean, this trick to basically take the idea of the neuron as basically the bits. You can actually use that also for your delay scheme, right? Like when you need to increase to go like beyond the 10 milliseconds, you can also use the same, and then you get instead of having to double the number of neurons, you'll just have to put the logarithm of the number of neurons. I mean, basically, you're designing something for inputs, right? Nothing prevents you from using the same input encoding scheme to delay your neurons, to basically put intermediate neurons instead of having to just put a neuron in the middle of every connection.
Let's see. For delays, maybe we'll talk after that. I'm not quite sure about how that would be implemented, but yeah.
Okay, thank you. Let's continue to the next talk.